This is part 3 in the series of lectures on calculating equilibrium concentrations from Kc. We will be working a third example in this case. In the previous lectures, we learned how to calculate equilibrium concentrations from initial concentrations and the value of Kc for an equilibrium reaction. In this lecture, as well as the next one, we will practice on 2 additional example problems. Additionally, in these 2 lectures, we will see how to incorporate the reaction quotient, Qc, into this type of problem. As before, please be sure to pause these lectures regularly so that you can work the problem along with me. This will be the best method for developing the skills for solving this type of problem. Let's review the procedure. First, once we have read the problem, we fill in as much of the ice table as we can. If a pure solid or liquid appears in the reaction, we do not need to tabulate its values. Second, if either the reactants or the products have an initial concentration of 0, then the reaction will proceed in the direction to form these species. Otherwise, we must use the value of Qc to determine the direction of reaction. Next, we have to introduce a variable in place of how much each concentration changes. Fourth, we then determine what the equilibrium concentrations should be in terms of their initial concentrations and the variables. And lastly, we substitute the algebraic terms into the equilibrium constant expression and solve. Please take a minute to pause this video and write down these steps so that you have them with you throughout the course of working this problem. Our example in this lecture is the decomposition of sulfuryl chloride, SO2Cl2. Consider the equilibrium, SO2Cl2 gas, decomposing to SO2 gas plus Cl2 gas. At 373 Kelvin, the Kc value for this reaction is 0.078. Initially, you have a container with 1.25 molar sulfuryl chloride, 0.16 molar SO2, and 0.24 molar chlorine. Calculate the concentration of all species once the system reaches equilibrium. As before, we begin by writing the Kc expression. In this case, the Kc expression has the concentration of the sulfur dioxide times the concentration of chlorine in the numerator, and it has the concentration of the sulfuryl chloride in the denominator. We begin by building our ice table. As always, our first row just restates the chemical reaction. This is followed by our initial concentration row, our change in concentration row, and our equilibrium concentration row. Our first step is to substitute in the values for all initial concentrations. 1.25 molar for the sulfuryl chloride, 0.16 molar for the sulfur dioxide, and 0.24 molar for the chlorine. At this point, we need to build the change row, but we don't know from the problem in which direction the reaction will proceed. To determine this, we must calculate Q and compare it to Kc. Recall that Qc takes exactly the same form as Kc. In this case, the concentration of SO2 times the concentration of Cl2, all divided by the concentration of the SO2Cl2. We then substitute in our initial concentration values. When we perform the arithmetic, we find that the value of Qc is 0.031. Since Kc, which is 0.078, is greater than Qc, which is 0.031, the system will react in the forward direction. This means the concentration of sulfuryl chloride will decrease, and the concentrations of sulfur dioxide and the chlorine will both increase. Since the stoichiometric coefficients are all 1 for this reaction, everything will change by the amount x. The sign is determined by the direction of reaction. we see that the sulfuryl chloride gets a negative sign because its concentration is decreasing, while both the SO2 and Cl2 get a positive sign because their concentrations are increasing. Finally, we can express the equilibrium concentrations in terms of initial concentrations and the changes. Again, we just read down each column and do what they tell us to do. For the sulfuryl chloride, we begin with 1.25 molar and we subtract off X, giving us 1.25 minus X for the equilibrium concentration. For the sulfur dioxide, we begin with 0.16 and add X, giving us 0.16 plus X. And lastly, for the chlorine, we begin with 0.24 molar and we increase by X, yielding 0.24 plus X. We are now ready to perform the algebra. As in the previous examples, please be sure to pause this video regularly and work this problem alongside of me. And again, do not try to rush this algebra. We start with the Kc expression, and we substitute in our equilibrium line from our ice table. This results in the quantity 0.16 plus X times the quantity 0.24 plus X, all divided by 1.25 minus X. The first step is to substitute in the value of Kc, or 0.078, and to multiply out the numerator. This gives us 0.16 times 0.24 plus 0.16 times X plus 0.24 times X plus X times X. Next, we clear the denominator and simplify. This gives us 0.078 times the quantity 1.25 minus X on the left-hand side of our equation. The right-hand side simplifies to 0.038 plus 0.40x plus x squared. We can now distribute on the left-hand side. This gives us 0.098 minus 0.078x. Now we can move everything over to the right-hand side, giving us 0.038 minus 0.098 plus 0.40x plus 0.078x plus x squared. Combining like terms, we simplify the right-hand side to negative 0.060 plus 0.48x plus x squared. Finally, we can move everything over to the left-hand side to put our polynomial into standard form. Once again, we have to use the quadratic formula to solve for x. Recall that for a standard polynomial, a times x squared plus bx plus c equal to 0, then the value of x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. From our quadratic, we see that a is equal to 1, b is equal to 0.48, and c is equal to negative 0.060. Again, don't forget to include that subtraction as a negative sign. We can now substitute these values into the quadratic formula. Please remember that you do not want to type this entire formula into your calculator at one time. It may seem like a shortcut, but it will ultimately lead to mistakes. Work each part step by step. First, we can square out 0.48, giving us 0.230. Next, we can multiply 4 times 1 times negative 0.06. This gives us negative 0.240. Lastly, the denominator has 2 times 1, which is equal to 2. We can now perform the subtraction under the square root sign. 0.23 minus a negative 0.240 gives us 0.470 under the root. We are now ready to take the square root and break up our fraction into two terms. The square root of 0.470 is 0.686. When we break up our fraction, please remember to keep the same denominator in both terms. Now we can divide. Negative 0.48 divided by 2 is negative 0.240. 0.686 divided by 2 is equal to 0.343. Since we have a second-order polynomial, we expect two possible roots, one due to addition and one due to subtraction. The first root comes from addition, negative 0.240 plus 0.343. This gives 0.103. Next, we subtract for the second root. Negative 0.240 minus 0.343 gives negative 0.583. Recall that x represents a change in concentration. As such, it must behave physically as a concentration. We know that we cannot have a negative concentration, and therefore the negative root must be ignored. We can now calculate the equilibrium concentrations. Recall that we found x to be equal to 0.103 molar. We can substitute this into our equilibrium row and calculate. For the sulfuryl chloride, we begin with 1.25 molar, and we decrease by x, or 0.103 molar. This results in an equilibrium concentration of 1.147 molar. For the sulfur dioxide, we begin with 0.16 molar and increase by x, or 0.103. The resulting equilibrium concentration is 0.263 molar. Lastly, for the chlorine, we begin with 0.24 molar and increase by x, or 0.103 molar. This gives us an equilibrium concentration of 0.343 for chlorine. Now that we know these values, the remaining step is to check our answer. When we substitute these values into the Kc expression, we get a value of 0.0786. Notice that this is not exactly equal to the Kc value we began with, and this occasionally happens. This is primarily due to rounding errors when solving the quadratic formula. As long as your value is fairly close to Kc, you obtain the right answer. We have now finished our second example. In this case, we saw that if initially we have some non-zero amount of each species in the equilibrium reaction, we must use the value of Qc to determine the direction in which the reaction will proceed to reach equilibrium. Once we have determined the direction, the process is the same as previous calculations. There will be one more lecture, which includes one additional example to solve.